Okay, class, today's lesson is 4.5, Exploring Properties of Exponential Functions. So today we're going to compare the relationship of an exponential relationship or function to a quadratic and a linear function. This is similar to what we did in grade 9, where we're going to use the graphing calculators to help us plot and discuss the differences both in the graphs and in the table of values. All right, so what you need to have, folks, is a graphing calculator open. So hopefully you can find a graphing calculator either on my website or I will show one here through the video. I'll just have to flip back and forth. So the first thing we want to do is reset our calculator. So we go to our calculator, we go second function plus 722. That defaults the sets, so it resets it. Then we go second function plus sign 4. Clear list, press enter, that's done. We go to y equals, make sure there's no equations in there. If there is, just press clear in the down arrow until you can get that. And what we're going to do, folks, is we will leave our mode as a float, okay? So instead of changing mode float to 2, we'll just leave it as regular. All right, so reading at the top of I'll just clear the history here, and then I'll go to the top of the lesson. So today we're going to use the technology. You can do this without technology, folks. I will show you that as we go, but I find it's easier to do it with technology. Being more familiar with the graphing calculator will help us. All right, so what we're going to do is it says here to enter the equations and information in y equals. That's where you enter the equations. Then we press graph. And second graph, ladies and gentlemen, will get us the table. So it'll tell us the table of values so we don't even have to substitute it in. So let's show you how it's done on the graphing calculator. So our first equation that we want to enter in is y equals 2x. So we've got the y equals already. We're going to go 2 and xt theta n button. Okay. Then we press graph. And we notice, hey, it's a straight line. All right, to find our table of values, we go second in graph. And all I'm going to do is line it up with the table that I have in my handout. So I'm going to make sure it's -3. So those are the values I'm going to transfer over to my handout. So I'm going to put them in. So looking at the y column, you're going to have -6, -4, -2, 0, 2, 4, and 6. Okay, so plotting those again for our graphs, just put an XY on, put a 2 and a -2 for a scale. And let's plot these points. Okay, so we start at the origin, and each point we can plot. So I'll start with 1, 2, 2, 4, 3, 6, and go backwards. Again, if you didn't want to use technology here, guys, you could just sub these x values into the equation and find y. Or you could just realize, hey, it's a linear equation. I'm starting at b, and my rise is 2 for every one run. So the slope would be rise m equals 2 over 1. So from your origin, you go up 2 over 1, up 2 over 1. And you're going to draw a straight line. Okay, let me just use my line to do that. Okay, I'll just quickly change the ends so that they have arrows on them. And I might just change the color so it's blue. Okay. Now it asks us to do what's called the first differences. The first differences is where you take the bottom one and subtract the upper. So I will show you the first. So you take 6, subtract 4, which equals 2. Okay. And when you do that, ladies and gentlemen, you're going to find in every case here that the first differences are the same. Okay, so the first difference are constant or the same, whatever you want to put down there. Therefore, the relation is linear. Okay, the graph of this linear relation creates a straight line. The general equation for the linear relation is y equals mx plus b, where there are no visible exponents. Okay? 3 ways to graph the line are table of values, okay, slope y-intercept method, and x and y intercepts. And these should be a review from last year, grade 9. All right. So the important thing that we want to carry away from this is any linear relation, the graph is a straight line, the table of values is the first difference is the same, and with the equation there are no visible exponents. All right, let's compare that to our second graph. Our second graph is y equals x squared. Hopefully you recognize that as our parent function for the quadratic. And what we should know about that is we see a visible exponent, and we know that our vertex is going to be 0 and 0. That's our parent function. Let's go back to the graphing calculator, and we're going to go back to y equals. We're going to clear that. And then we're going to go x, or xt theta n, and then hit x squared button. Okay, and then we're going to press graph. Okay, so we have our values there. And then if you want to get your table, you press second table, and here are your values. So let's enter those in. Okay. Again, if you don't have a graphing calculator, folks, just substitute these values into your equation and find the corresponding output or y value. So you've got 9, 4, 1, 0, 1, 4, 9. Taking a look, if we actually do the first, if we do the, pardon me, we do the first differences to start with. 9 subtract 4 is 5, and then 3, and then 1, and then -1, and then -3, and -5. Notice the first difference is, guys, shows your actual step pattern. So that tells us our step pattern is 1, 3, 5. That makes sense, folks, because A equals 1 in this case. All right, so the first differences aren't the same. How about the second differences? To do the second differences, you take the differences of the first. So 5 subtract 3 equals 2. All right. Before we get too ahead of ourselves, let's graph this, and we'll answer those questions. Okay, so you could just copy down the values or the ordered pairs, or you could do the, I find always doing the step pattern. We know it's, as we have our vertex at 0, 0, as we go over 1, we go up 1. As we go over 1, we go up 3. As we go over 1, we go up 5. 1, 2, 3, 4, 5. All right, so draw your nice parabola. And let's answer these questions. Okay. Notice in this case, the first differences are variable or not the same. Okay. And the second differences are constant or are the same. Therefore, this relation is quadratic. Okay. The graph of this quadratic relation creates a parabola or parabola. Okay, the most basic equation for the quadratic function is, or the parent function is, y equals x squared. That's where we always compare our transformations or translations from. Okay, the equation is often used to explain transformations, right there. All right, let's do a quick review of our quadratics, see if we have these memorized. Vertex form, ladies and gentlemen, y equals a x minus d squared plus k, where your vertex is going to be d, I apologize, d and c. My fault, guys. Back that up. Could either be H and K or D and C. I got one from each, so let's fix that. So it's going to be D and C. All right. Taking a look at standard form, it's y equals ax squared plus bx plus c. Okay, and that's easy to find the y-intercept, which is the c value. Whereas factored form is y equals a x minus r times x minus s. Okay, it's easy to find the zeros, roots, okay, x-intercepts, or solutions. And just remember they are the letters or variables r and s, opposite of what you see in your brackets. Okay, let's summarize quadratics, folks. So to summarize quadratics, we know that the graph is a parabola. We know that the table of values, the first differences are variable and the second differences are constant or the same. We know that the equation has an exponent of 2 when in standard and vertex forms. Factored form, you just have to think about it, guys, because it's x multiplied by x, which will eventually give you x squared. Okay, so it just doesn't visually show the x squared in that form. All right, moving on to the last one, the most important one is the one for this unit, which is called the exponential. Okay, so an exponential equation we've talked about in the past, but we really haven't given it that depth of detail in terms of course material. So that's why we're spending an entire unit on it here in grade 11. So let's go to the graphing calculator and plot this and see what happens. So I'm going to go to y equals. I'm going to clear that, and I'm going to change it to 2, and then I have to use the hat button, or the y to the x, that's get your exponent button of x. All right, everybody ready? Everybody's got that? Okay, let's press graph and see what happens. Okay, so we've got like a swoosh, or what we call an exponential curve. Okay? All right, so if we go to second graph, we can see our table of values. So let's put those in, and we're going to use fractions to help explain that. Okay, so let's go to our graph. Okay, so plugging in those, let's go to our handout. Let's plug in those y values from our calculator. So start at the bottom, so we'll go 8, 4, 2, 1, 1 over 2, which gives you the 0.5, 1 over 4, which gives you the 0.25, and 1 over 8, which gives you the 0.125. All right. So what we need to know, folks, is there's an interesting pattern, and I want to just use this opportunity to go back to the graphing calculator. And notice here on my table, if I press second table, notice as I go from the bottom to the top, my y values are getting halved each time. So 8, 4, 2, 1, half, a quarter, an eighth. I could keep going. What's happening to my y as I keep going? Keeps getting what? Smaller and smaller and smaller and smaller. And we're into exponential or scientific notation. And it just gets smaller and smaller. So what happens here, folks, is this indicates, if you look on this graph here, ladies and gentlemen, see how we start small, large, and we get smaller and smaller and smaller? What we have here is what's called an asymptote. It's a line that it's a curve that a line approaches that gets smaller and smaller, but never will touch or cross. Okay, so when we're graphing that, we've got to keep that perspective in mind. All right, let's go back and do some graphs here. So let's plot this, ladies and gentlemen. All right, so you've got x and y. Let's plot our regular scale. All right. What do I know is a key point is it's 0 and 1. Okay. From there, I've got 1, 2, 2, 4, and 3, and 8. 5, 6, 7, 8. From there, I'm going to half it each time. So this is going to be a half, a quarter, an eighth, a 16th, a 132, a 1 over 64. So I'm just going to approach my line. It's a curve. It's just going to go closer and closer with an arrow. And then it swoops up like that. Okay. So this is called an exponential. All right. Let's do our first differences and our second differences and see what happens here. So when we do our first differences, you're going to have 4, 2, 1, 1/2, 1/4, and 1/8. So what do we notice here, folks? It's a similar pattern. It's just shifted up one, right? Okay. Now we're going to do the second differences. Second differences. Taking a look at the second differences, we have 2, 1. Guess what pattern is still coming up? 1/2, 1/4, and 1/8. So let's just recap what we know so far. We know that it can't be linear because the first differences are not the same. We know it can't be quadratic because even the second differences aren't the same. So what we do is called a Y ratio. In order to do the Y ratio, guys, this might be new or you may not remember this from last year. You take the lower value and then you divide it by the upper value. Okay? All right? And we use the original Y values. So we go back to here. So basically you're going to take y to the 4th divided by y to the 3rd, which should equal y to the 3rd over y to the 2nd, which should equal y to the 2nd divided by y to the 1st. Okay, so I'll show you with a little bit of work here just so you can see. So we're going to take this and we're going to go right from here and we're going to go 8 divided by 4 equals 2. 4 divided by 2 equals 2. Okay, so you realize that your Y ratio in each case is the same. So that's how you can tell from a table of values if you have an exponential function. All right, let's take a look. The first and second differences are both variable. Okay, the Y ratio is constant. Okay, therefore this relation is exponential. The graph of this exponential relation creates what we call an exponential curve. Okay, the equation of an exponential relation has an exponent of x. Okay, we will examine exponential equations and relationships in future lessons coming up. Let's just summarize what we know. I'm going to add one other thing in here as well. So leave a little line by in here, okay? All right, so what do we know? The graph is exponential curve and there is an asymptote. Sorry, spell that right. Okay, so there's a what we call a horizontal asymptote. Okay, currently the horizontal asymptote in our example up here, if I flip up here, folks, is y equals 0. But again, when we do transformations and we shift up or down, that's going to affect by the c movement. Okay, so currently for the base function, it's going to be whatever y equals c is. Okay. All right. The other part we have to remember for exponential relations is the table of values. The first and second differences are variable, but the y ratios are constant. And the equation has an exponent of x. Okay. Next question or last question is, where do we see examples of exponential relations in the real world? Well, first of all, if we deal with acceleration, I know many of you guys are learning to drive or have your driver's licenses already. Acceleration and deceleration is one. When you think about population growth, or bacteria growth. Okay, think about bacteria. One big one is fruit flies. If you've ever had fruit flies in your house, you know that they grow very rapidly. So they grow what's called exponential. Other things that are going to be important to you later on is investments and borrowing. So whenever you invest money or when you borrow money, you're going to be paying interest exponentially, i.e. the more you borrow and the longer it takes to pay, the more interest you're going to have to pay. Or vice versa. If you invest money, the longer you put it in and the more you put in, the more interest is going to be earned on it. And the other thing I want to make sure you're aware of is what's called depreciation. Because many of you guys may want to get your own vehicle once you get your license and whatnot. Depreciation is the value of your car after you own it. So it's called the Blue Book value. You may have heard of that. And that's based on depreciation. In most cases, when you buy a car, it depreciates rapidly at the beginning and then it tailors off. That's an example of what we call a negative exponential curve, okay, or population decrease as opposed to a growth. All right. We'll talk more about these exponential relations and why it fits into society in our future lessons. But for now, here's your homework, page 243, numbers 1 and 2. Have a great day and see me if you need any help.